Hey everybody, so today we are talking about percent ionization, which again is just kind of a build on of our weak acids, weak base lesson, okay? So it's just another added step, really simple if you could understand kind of the conceptual idea of percent ionization. So what is percent ionization? Percent ionization is just simply how much an acid dissociates or ionizes or breaks down into its ions. So percent ionization is simply just put as the concentration of H plus over the concentration of the acid, which I'm just going to put as HA, times 100%. Okay, so this is just asking how much does an acid break down. Really, the strength of an acid is based on how much it splits up into its ions, right? HCl is a really, really strong acid. It completely breaks down into H plus and Cl minus. So if we have 1 molar HCl, when it splits apart, it's going to have 1 molar of H plus and 1 molar of Cl minus because it has such a high dissociation, such a high ionization. Those are the same thing. So in this case, where we have our equation up here, we would have the concentration of H plus, which is 1, over the concentration of our acid, which initially was 1, and we times it by 100, and its percent ionization is 100%. Okay? With all our strong acids and strong bases, they're going to ionize 100%. But in our weak acids and weak bases case, they are not going to ionize completely. They're really only going to be something like 2% or maybe even 0.03%. Okay, they hardly ionize, they hardly dissociate. So as you can see, if you have a high percent ionization, you're going to have a large Ka, right? If we have a 100% ionization rate, our Ka is going to be something like 1 times 10 to, 15th. Whereas we have a low percent ionization, like a 2% ionization, we're going to have a low Ka, like maybe a 1 times 10 to the negative 5th. And you'll see how all of those kind of correlate and work together, pH, Ka, percent ionization. But let's go ahead and let's go through a few examples of what you're going to see with these percent ionization problems. So our first example here, it says calculate the percent ionization of HC2H3O2, which is acetic acid, gives us the Ka, if it has a concentration of 1 molarity. So what we're doing here is we're finding percent ionization, which I'm just going to write as Pi. Okay, percent ionization, remember, is concentration of that H plus over concentration of the acid times 100%. So we got to find H plus and we got to find HA. Luckily, they already gave us HA. HA is just 1.00 molar. The HA in this case will just be the initial concentration of the acid. We've usually been finding acid at equilibrium, but here we're just using the initial concentration because we want to know how much this breaks down into H plus from our original. So we already have HA. We already have the concentration of the acid, acetic acid. But now we got to find H plus. If they gave us pH, that would be pretty easy. We could just take 10 to the negative pH, but they didn't give us that. The only thing they gave us was Ka. So if you think about this, whenever you see Ka, we're probably going to need to do some sort of ice table. So let's go ahead and let's do an ice table. So let's go ahead and break down this acetic acid. HC2H3O2, it's going to break down to H plus and into acetate, ethanoate, whichever you wish to call it, acetate or ethanoate. And then I'm going to put ice right here down the side. Like we said, the initial concentration was 1, and we don't have any initial concentrations for those guys because it hasn't dissociated yet. Minus x plus x plus x because they're on the right side with coefficients all of 1. And this is 1 minus x, x, and x. And remember, we're trying to find H plus. We don't care about this guy, okay? Remember, this HA is not at equilibrium. It is the concentration at the very beginning because we want to know how much it dissociates from the start. So now what we got to do is we got to do a little bit of calculations here to find our H plus. Remember, we could write a Ka expression of products over reactants. They're all aqueous. And then we could plug in what we know, right? We know Ka, they gave it to us. It was 1.8 times 10 to the negative fifth. We know H plus and C2H3O2 are both going to be X. And our equilibrium concentration of our acetic acid is 1 minus X. And then you start thinking, this would be really hard to solve for X if I had to multiply 1 minus X over to the other side. So let's see if we can assume that the change in X for our reactant is 0. Ka is really small, so it's not really going to dissociate a whole lot. So we could just assume this X is 0 and just make our equilibrium concentration 1. So let's go ahead and do that. It makes it a lot easier for us. And there you go. You got 1.8 times 10 to the negative fifth equals X times X, which is X squared over 1, which is essentially just 1.8 times 10 to the negative fifth equals X squared. Where when we solve for X, I don't know what we're going to get. I can't do that in my head. Let's do 1.8 second e to the negative fifth to the 1/2, if you don't want to do the square root sign. 0.0042, that is our X. So we have now just found our H plus, right? We have just now figured that this is 0.0042. We don't care about acetate, but it'd be the same, right? Because right now we just care about our percent ionization. So now we have our HA, which they gave us, which was 1, and we have just figured out our H plus. So now let's just go ahead and let's plug this in and figure out our percent ionization. So we're going to go ahead and we're going to take 0.0042 over 1 times it by 100%. 0.0042 divided by 1 times 100 equals 0.42% ionization. Not a whole lot, okay? So percent ionization for acetic acid is really small. That makes sense because the Ka is so small. It's not going to dissociate a whole lot. Let's go ahead and let's do another example where maybe we're given some different values. All right, everybody. So here I want you to calculate the pH of 0.035 molar HF if the percent ionization is 13%. Well, remember pH, if we want to find pH, we got to take the negative log of H plus, right? That'll give us the pH. So first of all, let's just see if this is a strong acid, right? If this is a strong acid, we just take the negative log of our concentration and we're good to go. Crap. HF is not a strong acid. It's a weak acid, right? Hydrofluoric acid. It is dangerous because it is super small, can get underneath the pores of your skin, but it's not strong. It doesn't dissociate a whole lot. So we're looking at this and we need H plus, and unfortunately we can't get it from that because HF does not fully dissociate. But they did give us percent ionization, right? And we learned that percent ionization equals H plus over the concentration of our acid times 100%. Well, this is nice, right? Because we already have percent ionization. It's 13. And look at that. They already gave us concentration of our acid, right? It was 0.035. So this is actually a relatively easy problem. Let's just go ahead and solve for it, get H plus, take the negative log of it, and we'll get our pH. So let's go ahead and do that. First thing I'm going to do is I'm going to divide by 100%. Let's just get this out of here and change that 13 back into decimal form. So now I have 0.13 equals concentration of H plus over 0.035. Square brackets, keep it consistent. Let me write this just a little bit better. 0.035. And this is 0.13. That's better. Okay, now to get H plus by itself, We multiply by 0.035 on both sides. Right? Those will cancel out. So my H plus is now 0.13 times 0.035. So my H plus is 0.00455. Cool. I got H plus. Now it's pretty easy to figure out pH, right? I'm just going to take negative log of 0.00455. And I can't do that in my head, so negative log 0.00455 because I'm not a robot. And you'll get a pH of 2.34. All right. So it's using things you know, like percent ionization, negative log of H plus equals pH, and using all those tools to solve these problems. I'm throwing in another wrench into your plans, right? I'm trying to get you to use your ice tables, use your equilibrium expressions, use your acid-base calculations, use your percent ionization to help you solve all sorts of different types of problems involving acids and bases. Let's go ahead and let's do this again, but this time let's try to switch it up with adding a little bit of base. All right, everybody, here I have NH3, a weak base. Has a pH of 12.35. If the initial concentration is 0.840 molarity, that looks weird. What is the percent ionization? All right, here I am dealing with a base now. So if you remember, with percent ionization of an acid, it was H plus over concentration of HA, which is good if we're dealing with acids, but we're not dealing with acids anymore. So again, when we talk about how strong an acid is as a high percent ionization, it creates a lot of H plus. But now since we're dealing with the base, we don't really care about H plus anymore. We care about the other half of that circle, which is OH minus, right? We don't care about H plus anymore. We care about the concentration of the OH minus. That's what makes a strong base. And we're not caring about HA anymore. We're caring about the base, which is symbolized simply as B, which is nice. So we just need concentration of OH minus. We need concentration of the base. So that's what we got to find now. So now we're not dealing with terms of acid. We're dealing with terms of base. So we have a weak base. It gives us a pH. That would help us find H plus, but it doesn't really help us find OH minus right now. Let's come back to that. And it says if the initial concentration is 0.840, cool. They gave us concentration of the base. We are good there. Now let's figure out how we can figure out that OH minus. Man, bummer. If we had POH, we would be able to figure it out, right? Because 10 to the negative pH gives us H plus, but 10 to the negative POH gives us OH minus. Well, you guys should be smart enough now that you guys can realize that I could change pH to POH at any time by taking 14 minus pH to equal POH. So let's do that. Let's go ahead and let's take 14 minus 12.35, and now I will get a pH of 1.65. Sorry, not a pH, a POH of 1.65. Okay, so now I have POH, no problem. Now let's go ahead and let's figure out OH minus, right? Now I could just do 10 to the negative POH, or 1.65, to get my OH minus, which if I take 10 to the negative 1.65, I get 0.0224. I just took it out to the number that rounded the nicest, so 0.0224. And remember, that is now my OH minus, so now I have both of my concepts to help me with this. So I'm going to go ahead and I'm going to put my OH minus 0.00224 over concentration of my base, which was 0.840, times it by 100%, 0.0224 divided by 0.840 times 100, and I get 2.67%, which is about what we'd expect for a weak base. Let's do one more problem where we got to use an ice table. All right, everybody. So here, I'm trying to trick you a little bit, so be on your toes a little bit here. So it says here we have 0.25 molar H2S. If the Kb is 6.22 times 10 to the second, what is the percent ionization? So first of all, we want percent ionization. So let's go ahead and let's just write out our percent ionization equation. We're dealing with the acid here, right? It's H2S. And it's going to be H plus over HA times 100%. Okay? We already have HA. They gave us the concentration of HA, but we need the H plus, right? They didn't give us pH, so we can't just take 10 to the negative log of that. But they did give us Kb. Kb doesn't really help me here, right? I'm dealing with a weak acid. I need Ka. But I mentioned this just briefly. We have a very, very easy way to go from Kb to Ka, okay? And it's because of our dissociation of water, all right? I know I briefly touched on this, but I want to go back to it again. That's why I'm doing this, right? We really need Ka. If we're dealing with the acid, we need Ka. That's why we use this equation right here. Kw equals Ka times Kb. Kw is just the dissociation of water. Water doesn't really dissociate that much. It's really, really small. They will give you this on the AP exam. The dissociation of water is 1 times 10 to the negative 14th. Okay? So if we know Ka or Kb, we could get the vice versa or opposite of them because of this equation right here. So luckily we know Kb, which is 6.22 times 10 to the second. And now we can figure out Ka pretty easily. Let's go ahead and take 1 times e to the negative 14th divided by 6.22 second e to the second, and you'll get a Ka equal to 1.61 times 10 to the negative 17th. So just be aware that they might do that to you. I don't see it too often, but they might do something where they give you Kb and they want you to get Ka because they gave you an acid. So be aware of that. Just know how to make those conversions, right? You know how to go from pH to POH to OH to H+. You should be able, no problem, to go from Kb to Ka by using that Kw equals Ka times Kb equation. So now that we have Ka, we could probably do something like an ice table to help us figure out H+. So let's go ahead and do that. Remember, H2S, it's only going to donate 1 hydrogen at a time. All of them are monoprotic. So we're going to have ice right here. Our initial concentration is 0.25, 0 minus x plus x plus x. 0.25 minus x, and let's just skip the dancing, right? We know this x is going to be 0. Look at that Ka. That is such a small Ka. We know that x is going to be 0, so let's just get rid of it right off the bat. Now we got to use our equilibrium expression in order to solve for H+, which is simply Ka equals H plus over HS minus over H2S. And luckily we have all these things. The Ka was 1.61 times 10 to the negative 17th. H plus was x. HS minus was x. And hydrosulfuric acid was 0.25. Do a little algebra here to solve for x. You know these are going to become x squared. We're going to have to take 0.25 times 1.61 second e to the negative 17th. We're going to have to square root that answer and get an x of 2 times 10 to the negative 9th. So our x was 2 times 10 to the negative 9th, which remember is our H plus. So now we have both of them. We have our H plus and our HA. So let's go over here to finish off that. Our H plus is 2 times 10 to the negative 9th. Our HA, or our concentration of our acid, was 0.25. We're going to times it by 100. This is going to be a really, really small percent ionization, but hey, we're going to do it anyway. Okay, so this is just pretty much not going to change into anything. 8.02 times 10 to the negative 7th %, okay? I'm going to be honest with you, I just came up with this on my own out of the blue. So that's a really low percent. You usually won't see anything like that. But that's the percent ionization of hydrosulfuric acid. That would hardly do anything. That's like dipping your hand in a, I don't know, in a mud puddle outside. It's going to probably dissolve your skin the same as this one will. Alright, so that is percent ionization, okay? Just another equation. Make sure you're using your skills of Ka, using your skills of pH, using your ice tables to help you solve problems like this, okay? That's it for today, guys. Have a good one.